Morning, sir.
Yes. Hello.
Hello, sir. We can hear you. If you can
Yes,
switch
yes.
on the video, it will be useful.
Sure, sure.
Sir, your device is muted.
Tell me when to start.
Sir, we can start. We are ready.
Good morning and welcome all. We'll be starting this session now. On behalf of Wilson College Physics Department and IAPT Sub-Regional Council, I welcome you all again. I also welcome today's speaker, Dr. Dinesh Kumar, and he is going to talk us about gravity anomalies and its measurements and interpretations. Friends, Dr. Dinesh Kumar is a professor and chairman of Department of Geophysics at Kurukshetra University. He has multiple assignments. He is also a director of IQAC at Kurukshetra University. Similarly, a dean of Research and Development Wing of Kurukshetra University. He is also working as the coordinator for NAC steering committee at same university, Kurukshetra University. He was also a chairman for Department of Geology at Kurukshetra University from December 2011 to December 2014. Mainly, the specialization of Dr. Dinesh Kumar is seismology and seismic hazards. He has a teaching experience of more than 33 years, and he has in his credit about 95 papers, research papers, out of which 52 are in peer journals and 43 are from conferences and seminars. He has guided and supervised 8 PhD projects, PhD theses, and also is having credit of supervising 60 MTech dissertations. And at the same time, he completed 5 projects till today, out of which 3 were at national level from DST and 2 are from international level. As I said, he is a man working for working as a IQAC director but at the same time, he is also assisting the other colleges and university. He is also a member of IQAC at Chaudhry Bansilal University, Bhiwani, Chaudhry Ranveer Singh University, Jind, Dayal Singh College, Karnal, J.C. Bose University and University of Science and Technology, Faridabad, Dr. B.R. Ambedkar National Law University, Sonipat, and Sri Vishwakarma Skill University, Paliwal. So welcome you, sir, and over to you.
Thank you, Dr. Bhole, for introducing me. Am I audible?
Yes, sir.
Okay. Good morning to all of you, and I am thankful to Dr. Bhole for introducing me so nicely to the audience. So, before I start my presentation, I am thankful to Dr. Mahesh Shetty also, who has invited me for delivering a talk on gravity anomaly, its measurement and interpretation techniques. So I hope that all the students will enjoy this talk. So let me share my screen, then I will proceed.
Sir, I will request you to adjust this video camera. Your face is not completely visible.
Okay, ultimately I will off
yes,
this
yes,
video
sure.
camera.
Now it's okay. Now it's okay. Yes, visible.
Is my screen is visible?
Yes, sir, it is visible
and we can use.
Okay, thank you all. So my today's topic is gravity anomalies, measurement techniques, processing and interpretation. So as I belong to geophysics department, so little bit first 2-3 slides I will tell to the students that what the geophysics is about, and then what are its methods, and then particularly I will emphasize on the gravity method of the geophysics, which explores the interior of the earth. So geophysics mainly that it is to study the interior of the earth with the help of the principles of physics. So to discover the hidden features of the interior of the earth, so it includes the oil, groundwater, minerals, or some other aspects also like earthquakes and volcano. The difference between physics and geophysics is that basically we are using the principles of physics, but now our system is earth, not any other system, but it is the earth. So we are applying the principles of the physics to the earth, and purpose is to study the deep interior of the earth. As the students might be knowing that the radius of the earth is around 6,400 kilometers. So directly, no one can go inside the earth to see that what is there at what depth. So indirectly, we have to send some signal inside the earth and record that signal at the surface. And by analyzing those signal, we have come to know that what are the internal structure of the earth. So whatever boundaries we know about the interior of the earth, like crust and mantle and core boundary, what is the depth of the boundary between the crust and mantle and core. All this has become possible because of the application of the geophysics, principles of the physics when we apply to the earth to study the interior of the earth. So that is the geophysics broadly. So like this man is trying to observe the vibrations inside the earth, that where there is a water, where there is oil, where there are some minerals or ore bodies. So ore bodies, for student perspective, I would like to say that ore body is that geological body from where we extract the minerals which are useful for the society. So ultimately, one of the purpose of the gravity method is that to locate and to the depth, at what depth the ore body is available, so that mining can start in that area to extract the minerals. So physically, as this man is trying to observe the vibrations that he wants to listen that where there is a oil, where there is a water, but the man has a limitations. He cannot listen up to the deep interior. So instead of this man, what we do, we send some signal inside the earth and then record those signals at the surface, and then we analyze those signals to know about the interior. So, like for example, seismology, as I said, this is the one of the important branch of the geophysics. We know that the inner core of the Earth is solid. Inner core is at about, you can say, 5,000 kilometer from the surface of the Earth. But how do we come to know that inner core is solid? Because as I have said that we cannot go directly inside the Earth because of increase in temperature and pressure. We cannot go inside the earth. Then how do we know? So this is, you can say that whenever earthquake occurs on one part of the earth and we record those waves at the other part of the earth at the surface. So by analyzing these waves, we can say that through which medium these waves have passed through. What is the nature of that medium? Whether that nature is solid, nature is liquid, or nature is fluid. So whatever it is, so by analyzing the waves of the earthquake, which have been generated naturally, and they have passed through the deep interior of the earth, and then they have been recorded at the surface. So by analyzing these seismograms or record of the earthquakes, we have come to know that what is the depth of the inner core and it is a solid. This also, by analyzing these waves, we have come to know that inner core is solid while the outer core is the fluid in nature. So this is the one example that how exciting this branch of geophysics is, that we want to know the depth of the inner core which we cannot see directly, but we are analyzing those by we are getting the depth of the outer core, inner core, by analyzing the signals which are coming from the earth. So that is all about the geophysics. So when we talk about the geophysical methods, so in geophysical methods we can categorize into these two methods. One is what we call natural source geophysical method, and another is the artificial source geophysical methods. In natural source geophysical methods, we do not send any signal naturally. We do not artificially, we do not send any source or any signal. Like in case of earthquake, so source is natural because we are not sending any type of the waves inside the earth, but it is a natural occurring. So when we record at the surface, then we analyze those waves. Similarly, gravity method. Gravity method is also a natural source because we are measuring the gravitational value at the surface of the earth with the help of our instrument, which we call gravitymeter. In magnetic method, we measure the magnetic field of the earth. In seismology, as I have said, we measure the earthquake waves. But we are having a artificial geophysical methods also. In seismic method, what we do, we send the waves inside the earth by exploiting some dynamite at the surface. Those waves generated by the dynamite, like ONGC is doing oil exploration using the seismic method. We send the signal by exploding the dynamite at the surface, and those waves will go inside the earth and it will be recorded at the surface. Similarly, in electrical method, we send the electric currents inside the earth. In exploration seismology, seismic methods, all these are the artificial source geophysical methods, and today we will be focusing on the gravity method only, which is a natural source geophysical methods. And in addition to that, in the methods which I have just shown, given the name, these are the surface geophysical methods where our instruments are on the surface, source is also on the surface. But there is another set of methods which we call well logging. In well logging, we drill a borehole at the surface up to certain depth. Then we insert our instrument inside the borehole. And then we record the physical properties of the interior of the earth material, which whatever is available, whatever is there, we record the physical properties and then analyze them. So this is known as a well logging method of the geophysics. So in every geophysical method, we are exploiting the physical properties because we know that Earth is not homogeneous, meaning thereby is that the physical properties are changing with depth as well as laterally also, horizontally also. So wherever there is a change in the density, it means the gravity value will change, mass will change. So that variation has been exploited in the gravity method. Similarly, variation in the magnetic properties of the material of the Earth. That is the basic principle of the magnetic method. So every geophysical method is exploring the or exploiting the variation in the physical properties of the Earth material. So gravity method basically is used to know the depth of the ore body, to know the dimension of the ore body. Ore body means that from where we extract the minerals. And it has some application in oil exploration also. Because when we do the oil exploration, like ONGC, Oil India Limited, or some other companies they are doing, so they want to know some geological structures like fault and fold, whether they are present or not. So gravity method is a useful method to have some idea that in which region the fault is there or geological structures are there where there is a possibility of oil can be there. Similarly, in magnetic method, in seismic method, we go for the contrast, acoustic impedance contrast, that is a density into velocity. For groundwater exploration, we use the electrical method. In this electrical method, we send the electric current inside the earth and then measure the resistivity. So like in some area that if we want to drill a well for water, we drill a well, but there is no water. So by using electrical method of geophysics, we can tell the farmer that if you drill at this particular point, then there may be a possibility of the water. So by measuring the resistivity, by measuring the electric current at the surface, in geophysical electrical method, we can say that on these locations, possibility of water may be there. So this is just a pictorial presentation that how seismic method is there. So this is actual scenario. This is our instrument. These are the cables. So with the help of this, it is sending the signal inside the earth. So when signal goes inside the earth, it reflect back or reflect back depending on the contrast in the velocity or in the acoustic impedance. So we are recording the signals at the surface. So by analyzing those records, we will come to know that whether oil is present and if at what depth it is present and what is the depth of the bedrock. Similarly, in electrical method, we send the electrical current inside the earth with the help of our system, our instrument, which is on the surface. So this is the actual scenario on the surface of the earth. Cables are there, electrodes are there. So we are sending the current inside the earth and then measuring the uh, uh, voltage as well as resistance and the resistivity. So it will tell us about the possibility of the groundwater inside the earth. Similarly, in gravity method,
Sir,
so this is our
sir,
hello.
can I mean, will you take questions now or later?
Uh, what is your practice? Means maybe later
No,
on.
it is whatever is convenient to resource person. So
Okay. So let us say afterwards, after the completion of lecture,
okay, sir.
then that will be more appropriate, I think, one by one.
Okay, sir. Fine.
Okay. So in gravity method, this is our instrument that is we call gravity meter, which is used to measure the gravity field of the earth. And this is on the actual earth, actual case on the surface of the earth, gravity meter, and we are measuring the gravity value at the surface. So in every geophysical method, these three steps are there. One is that we go to the field to acquire the data. If we are going for a gravity data, we take our instrument because it is a portable instrument. We go to the field and acquire the gravitational field. Then we do the data processing, signal processing, whatever it is. So at the lab and then the data interpretation. So these are the basic steps of any geophysical method. So if we consider, let us say, digital signal processing and versus earth system. So in digital signal processing, so this system may be anything. It may be a filter, it may be any instrument. So in an instrument, we have some input and we record some output. But in case of geophysics, system is replaced by the earth. So We give some input like in electrical method. There is a response of the earth. We record some output, and by analyzing that output, we tell something about the earth. So in some cases, input is unknown. Like in case of a gravity method, it is a natural. We are not sending any energy or any signal inside the earth in gravity method. We are just measuring the output. We are measuring the gravitational field of the earth where input is unknown and response of the earth is also unknown. So, but we have an output in our hand. So by analyzing output, we have some idea what is the nature of the earth and what is the nature of the input also. So in gravity method, basically this is a very broad picture. It may clear to the students also, because you see that this represents the surface of the earth and this is the interior subsurface. So there is no presence of ore body here. There is no presence of ore body here. Density is rho 1. So if we measure the gravitational field here at the surface by putting our instrument here, then here, then here. So when we plot this gravitational field, so it is almost a straight line. But whenever there is some ore body present means there is a excess of mass as compared to the surrounding, or deficiency of mass in that region as compared to the surrounding. So for ore body, the density may be different from the surrounding. It means that there is a density contrast for some localized region whenever there is a presence of the ore body. So ore body, in general, it may be having a higher density as compared to the surrounding. In some cases, it may be having a lower density as compared to the surrounding. Main point here is that there is a lateral variation in the density. So that lateral variation in the density will be depicted in the gravitational field which we measure at the surface. So we put our instruments on the surface of the earth and move it first here, then here, then here. So when we record it, when we plot the record of those gravitational field, so if there is a ore body, it will be depicted here like this. So when there is a no ore body, so it means that there is a no variation in the gravity from one point to another point. So there is a no excess mass or no deficiency of mass, no variation of density. But whenever there is a variation in the density, that will be depicted in the gravitimeter reading. So by analyzing this, we can say that at what depth the ore body is there, and what is the dimension of the ore body, what is the aerial extent of that ore body in the subsurface. So this is the, you can say, the basic idea of a gravitational method. But when we do the actual things becomes a little bit difficult also sometimes, because our terrain is not horizontal as we are depicting here. Our surface is also not horizontal. So the basic principle of gravity method is a well-known Newton's law, that we all know that this force of gravitation can be written in this way. And second law of Newton can be written in this way, that A is the acceleration, m is the mass. But now we apply this law to the earth. In case of earth, one of the mass is the mass of the earth, that is capital M, and another mass is any object which is lying on the surface of the earth. So between these two masses, the gravitational force is given by this, and then R, this capital R becomes the radius of the earth, distance between any object on the surface and the center of the earth, that is R. And second law, because now small g, as you know that it is a acceleration only, but acceleration due to gravity, due to earth. So for two bodies, for two objects, we use the symbol A, but when one of the body is earth itself, then we use the symbol small g. And capital G, you know that it is a gravitational constant. So little bit simplification. So acceleration due to gravity can be written as gm by r square, where capital M is the mass of the earth. So this is the basic principle of the physics which we are using, which we are exploiting in case of gravity method of earth. So this is a simple cartoon which showing the difference between the speed and acceleration. Speed is the difference in the position with time, and but it is the difference in the speed with time, that is the acceleration. So as I have said that the basic principle is this one, G is equal to Gm by R square. If students may note that in this formula, the gravitational or small g does not depend on the mass which is falling on the surface. So that's why you might have studied in physics that if we drop a piece of paper and a piece of a stone from any height, so according to this formula, they will be reaching at the same time at the surface, provided there should not be any other forces. So if these two types of the object, piece of paper as well as an piece of stone, if you drop them under the force of gravity only, so they will reach at the same time. So that is the physical interpretation of this formula, physical meaning of this formula, that acceleration is not depending on the mass of the object that is falling on the surface. In gravity method, the basic challenge is here is that these are the broad variation in the density of the earth materials. For air, for water, then for sedimentary rocks or for sandstone, shale. If you can see that the variation is very small in the density. If variation is small in the density, it means that the variation in the gravity field will be very less. Major challenge in the gravity method is that how to measure this change in the small variation in the density. So we are not interested in the absolute value of gravity. We are interested in the relative gravity. Because of a very small variation in the density values, our instrument should be very sensitive. It should be very sensitive. So like in this case, this is again a cartoon that this area indicates that the density is low, this area indicates the density is high. So naturally, in this case, the gravity value which we are measuring at the surface, that will be more. So, but if we are able to measure the absolute gravity, on the other hand, even if we measure the density contrast, that means the density of this shape will be different from the surrounding. So again, we will be getting the same one. So we are interested in the relative gravity. Relative gravity means difference of the gravity value at a particular point with respect to some other point. So that is a relative gravity. So we are not interested in the absolute gravity because the variation in the density is very small, and it is always a challenge to measure that small variation in the density. So this is a typically more geological picture that if there is a ore body, so the density is different from the other. Density means, whenever I say density, it means that mass, because you know that mass and density, they are directly related. So okay, so mass of this ore body will be different from the surrounding, and that mass will affect the gravity value at the surface. So when we measure the gravity value at the surface, that mass will be depicted here, ore body. This is one of the ore body. This is what I say that fault. This is one of the geological structure which we see during the oil exploration. So in this area, the density is different as compared to on this side. This is a fault. So when we measure the gravity value at the surface, our reading will be like this. So from the profile itself, from the reading itself, we can say that whether in the subsurface there is a fault, geological fault, or in the subsurface there is some ore body. So once we say that there is some ore body, then we want to know that what is the depth of the ore body. Then we want to know that what is the areal extent of that ore body in the subsurface. So this is a unit which we use in the geophysics. So one Galileo, GAL, this GAL means Galileo, after the name of that scientist, and acceleration is centimeter per second square, and ultimately because variation is very small, so the popular unit in geophysics for gravity is the milligals. So one gal is 1 centimeter per second square, and 1 milligal is 0.001 gal, and another unit is the gravity unit. So 1 milligal is 10 gravity units, and ultimately we take the readings in the gravitymeter in this unit, milligals. So milligals is 10 raised to power minus 3 gals. Gal means centimeter per second square. So we know that our Earth is not a completely spherical ore body. So on the equatorial radius is more as compared to the polar radius. So there is a difference of, that 21 kilometer in the radius. So if we measure the gravity value in the polar region or in the equatorial region, they are not same. These three factors are contributing. Distance factor, because in case of a sphere, we know that the mass of the sphere can be assumed as if it is concentrated at the center. So in the equatorial radius is more, therefore gravity will be less according to the this formula. Gravity will be less in the equatorial region. But there is a mass factor also, there is a rotation factor also. When we combine the contribution of all these three factors, the net effect is that gravity value in the polar region is more. So that is a 983,000 milligals at the polar region and 978,000 milligals at the equatorial region. So gravity at the pole is more as compared to the equator. So this all of you might be knowing, particularly students also, that how the value of g varies with height and the depth. So as we move away from the surface of the earth, the gravity decreases. And ultimately, if you move further, and you might be knowing the concept of the escape velocity also, that ultimately the gravitational effect becomes zero at a particular height. And when you throw any object with the escape velocity, it will go beyond the gravitational effect of the earth and it will never fall back to the surface. So, so it means that gravity is decreasing as we move away from the surface of the earth. And similarly, in case of a homogeneous earth, even if we moving towards the center, the gravity is decreasing provided earth is homogeneous. So this is a topography of some region, let us say, because topography is not flat. Sometimes it is a horizontal and there are mountains also. So we measure the gravity value at different points. So then it is a absolute gravity. But in the relative gravity, first we measure the gravity value. This is our gravity meter. We measure the gravity value at this point and then at the top of the mountain. So difference between these two will be a relative gravity. And at all other points, we are measuring the gravity value with respect to this one. So that is a relative gravity. So why it is important? Because suppose that there is a spherical ore body in a spherical shape, its depth is 25 meter and radius is 10 meter. So when I plot this, it will be like this. And the maximum anomaly or maximum gravity is 0.025 milligals at this point. So this is equivalent to 1 part in 40 into 10 raised to power 6. So we want to measure so much accuracy in case of a gravity method in geophysics to explore the ore body. So that's why it is very difficult to measure the so small variation in the gravity. Why there is a very small variation in the gravity from one point to another point? Because the density variation in the different types of the rocks are very small. So that's why the variation is very small in gravity. Our instrument should be very sensitive to measure that one. So that's why we go for the relative gravity. So as far as absolute gravity is concerned, these are the simple methods we can measure. Now you can see that if we drop a ball or drop a piece from any height, we can measure the gravity value using this formula. But whether this G is accurate or not, it depends on the how accurate we have measured the X, that is the distance from which the object has been fallen, and how accurately we have measured the t value, that is a time taken by this object to reach at the surface. So if there is any error in the X, any error in the t, our G will be wrong. So that's why, so to as far as geophysics is concerned, to measure X as accurate as to 1 part in 10 raised to power 6. Similarly, to measure time, 1 part in 100 into 10 raised to power 6. So much accuracy is required in case of a geophysical gravity method to locate the ore body, to locate the minerals or some subsurface characteristics. Because in geophysics, we need this type of the accuracy in the value of G from one point to another point. So that's why we are not going for the absolute gravity, and these are the other methods of absolute gravity, pendulum methods. It is like that free fall mass from one height and we can measure G here. But again, it depends on that how accurate we are measuring T and how accurate the measuring L. And presently the gravimeters are based on the spring mass system. In every gravimeter, there is a spring mass system. Wherever there is gravity is high, this mass will be stressed as compared to the normal position. But to measure the G accurately, T should be very accurate, and K, that is a spring constant, and it has been found that K cannot be determined accurately, which is required as 1 part in 40 millions. So that's why now it will clear that why we are going for the relative gravity. Suppose that we measure the gravity at site 1, that is a G1, T is let us say T1, spring constant is same. It may not be accurate, but it is the same. Then we take our gravimeter at another site, then it becomes G2, T2. So G1 and G2 are not accurate because K is not accurate. So whatever error is there in the value of k, that has been propagated in the value of g1. The error in the value of same error has been propagated in g2 also. So if we say individually g1 is not correct, g2 is not correct. But when we take the difference, because same error has entered in the value g1 and g2. So individually they are not correct, but when we take the difference, then it becomes correct, because difference between the G1, G2 is correct, because same error has been propagated in the value of G1 and G2. So therefore, difference will be correct. The individual values are not correct. So that's why we always go for the relative measurement in the gravity method in geophysics. So this is one definition that how we define, because it is important to move further. If we define, if our earth is homogeneous, our earth surface is like this and dash line, we call it a normal spheroid. But if we consider that earth, there is a topography, there is a ocean, there is a mountains, then actual surface is what we call geoid. This is the topography. So on normal spheroid, when there is no variation in the density, we can calculate the theoretical gravity at the normal spheroid using this formula. Phi is the latitude and g is the gravity value at the equator. So in this formula, you can see that there is a no term of the density, because while deriving this formula, it is assuming that Earth is homogeneous, there is no variation in the density. But if Earth is a for stationary sphere, we can calculate gravity in this way. And at the normal spheroid, we can calculate in this way. That is a theoretical gravity value, assuming there is a no variation in the density. So in the gravity method, the major challenge is that to measure the variation in the density. But what happens that when we move from one point to another point, the topography is not same. It is a, let us say, very, so at this point, we are near to the center as compared to this point. And we know that the gravity is universally proportional to the square of the distance. So it means that at this point, the gravity will be low as compared to this point because of this distance factor. So gravity has been changed from this point to this point because the distance from the center has been changed of the gravimeter. This is not our objective, because we want that gravity should change from one point to another point only because of the density contrast, not because of the any other factor. So if any factor which is contributing in changing the gravity value from one point to another point, that becomes noise for us. That becomes the noise in the gravity data. So all these are the factors which are changing the gravity value in addition to the density contrast. Drift, there may be a drift in the instrument, tides, elevation as I have said. Similarly, there is an extra mass which is lying between these two. So that will increase the gravity value from the other point. So all these factors which are contributing in changing the gravity value in addition to the change in the density, that will be a noise, because ultimately our objective is to know the change in the gravity value only when there should be a change in the density. Ultimately, this will clear. Here we put our gravimeter, take the reading, then here we put our gravimeter. So this is a sea level. This is sea level. So what we want to know that we want to project all the values at the same level. Then we compare them. Then we compare them whether they are changing or not. Now from this point to this point, the gravity is changing because there is extra mass. Mass will increase the gravity value. So there is a increase in the elevation that will decrease the gravity value because of this law. So all these factors are noise for us, and our target is to measure the change in gravity value only due to the subsurface density contrast. Subsurface means the surface below the surface of the earth. Only that is our signal. Otherwise, all things are the noise. So that is what we do during the processing of the data. We remove all these factors from the gravity data. So these are the corrections to remove the effect of the all factors affecting the gravity values. So these are the corrections: drift correction, latitude correction, free air correction, Booger correction. Booger is the name of scientist. Then terrain correction, isostatic correction, tidal correction, EOTOS correction. So for every factor except density contrast, we apply some correction. So drift little bit, just I give some only a very broad idea. Drift means that if we take a reading at a particular station in the morning hours, the value will be G1, let us say. But at the same point, if we put our gravitymeter in the evening hours, we expect that gravity should be same. At the same place, gravity should be same. But it has been found that gravity will change at the same point, at the same site, only difference of the time. So within a 24 hours, the subsurface geology is not going to change. It means that whatever change we have observed at the same place within 24 hours, that is because of something else. So that is what we call drift in the instrument. So why there is a drift in the instrument? Because our spring is not perfectly elastic. Because in every gravitymeter there is a spring mass system. And if our spring is not perfectly elastic, so it may change. There may be some effect of the temperature also on the spring mass system. And there may be a mishandling of the gravitymeter also. So this is a drift in the instrument which we can remove by reoccupying the one station again and again. So this is our base station on the surface. First we take the reading here. We move to the next station, take the reading, move to the next station, move to the next station. Then we come back to the same station to note down that how much gravity value has been changed at the same place with time. So once we know that drift rate, we call it a drift rate, that the change in the gravity value at the same point with time, then we can correct all other readings. So we can remove the drift component of the reading which have been there due to the drift of the instrument. So the latitude correction, as we know that gravity will change from pole to equator. Again, if we are doing the survey from pole direction to the equator direction, gravity value will change. This change in gravity value will not be due to the subsurface density contrast, but it is because of the distance. So for that, we apply the latitude correction. Similarly, for free air correction, so we know that as we move away from the surface of the earth, the gravity value will decrease. So this decrease in gravity value has nothing to do with the density contrast in the subsurface. This is because of the change in the elevation of the gravitymeter from one point to another point. So for this also we have to apply some correction that is known as a free air correction. And with simple mathematics, it has been we have come to know that for every 3 meter upward from the surface of the earth, the gravity decrease about by 1 milligal. So this we know that 0.3086 milligal per meter gravity value will decrease. So we know this elevation of the gravitymeter from mean sea level. We know this rate of the decrease in gravity value. So we can calculate the free air correction and give to the observed value of the gravity. So this is the observed value of gravity with the gravitymeter. This is a drift correction we have applied. Then we apply the free air correction using this formula. So once we apply the free air correction, it means that we have projected the value from this point to this point. Similarly, from this point to this point, this point to this point. So free air correction takes care of the elevation difference of the gravitymeter from mean sea level. But then there is a mass also. This mass is also present between the position of the gravitymeter and the mean sea level. This mass will increase the gravity value. Our ore body is below mean sea level. Ore body is below mean sea level. So the mass which is lying between the mean sea level and the position of the gravitymeter, that will increase the gravity value. Again, this is a noise for us. So for this, we apply a Booger correction. So that is a 0.0419 rho h. So we apply the Booger correction, then free air correction. So in this way, because ultimately our aim is that to project all the gravitymeter readings at the mean sea level. What will be the gravitymeter reading if our gravitymeter position at the mean sea level? But because of the topography, our gravity meters are at the different elevation. When there is a different elevation, mass will be there, change in the elevation will be there. So we are removing one factor by another factor. Ultimately, when we project all the values at the same level, so then we can compare them. After that, if there is a change, if there is a variation, then we can say that that variation is because of the subsurface density contrast. So this is like that we cannot compare for student purpose. I am explaining that we cannot compare the knowledge of a student of first year, knowledge of a student in physics, first year student with the knowledge of a student in the second year, because they are not at the same level. So we can compare the knowledge of physics of first year students among themselves. We can compare knowledge of physics first year students among second year students, but we cannot compare first year with the second year. So ultimately, we have to bring all the gravity values at the same level by removing all the factors except density contrast. So then terrain correction, it is a basically where the topography is not flat. There is undulations in the topography. For that also we apply some type of the correction, that is a terrain correction, and this is because of these are the derivation of the terrain corrections. Naturally, we are not going into the derivation. So we little bit skip, but there is a correction due to the topography. Then gravity anomalies. So there are two types of the gravity anomaly. One is the free air anomaly, and then another is the Booger anomaly. So free air anomaly, this is the observed value of the gravity. We apply the drift correction to remove the effect of the drift of the instrument. We apply the free air correction to remove the effect of the elevation difference of the gravity meter. Then this is a theoretical gravity value, which we can calculate from the formula which we have explained on the normal spheroid. So after applying all the corrections and then subtract it from the theoretical gravity value, then we call it a anomaly. This is a free air anomaly. We have not applied the Booger correction here. It is a free air anomaly. Anomaly means deviation from the normal position. So that will be a typical free anomaly curve. And this is a, let us say, our topography of a area. This is our mean sea level, this dotted line. Suppose that there is excess mass here or there is a deficiency of mass here. Excess mass means that its density is more as compared to the surrounding. Deficiency of mass is that its density is less as compared to the surrounding. So we are doing the gravity survey. First take reading here, then reading here, reading here. Because gravity meter is portable, so we take our gravity meter to the field and do the gravity meter reading at different points on the topography. When we apply the correction, we have projected all the readings on the mean sea level mathematically. So then we plot this one. This is a free anomaly curve. You can see that wherever there is excess mass, its value is away, and wherever there is a deficiency of mass, its value has been decreased. So in this way, by looking at the profile, we call it a profile. We look by looking at the gravity profile, we can say that where is the excess mass and where is the deficiency of mass. So where there is no excess or deficiency, it is almost normal. So this is a free air anomaly. But when we apply the Booger correction also, then it becomes a Booger anomaly. So basically the final product of any gravity survey is the Booger anomaly. We conduct the gravity survey, apply all the corrections, subtract the theoretical gravity value from that, then whatever is left, that is a Booger anomaly. So Booger anomaly can be written as free air anomaly minus the Booger correction. So again, this is the difference between the free air anomaly and Booger anomaly. So ultimately, this solid line is our basic product or final product of any gravity survey. We interpret this later on that, but by looking at this profile, we can say that at this position, there is some excess mass. At this position, there is some deficiency of mass. So this is a typical Booger anomaly profile. So this is a summary of corrections which I have discussed so far that this is a topography of area. This is, you can say, deficiency of mass in case of a marine gravity survey, and this is a mean sea level. So we apply a free air correction during a land gravity survey. We apply a Booger correction, At sea, we apply a Fourier correction is not required because in the coastal region, we are already at the mean sea level. So at mean sea level, H becomes 0, so no need of the Fourier correction. But Boer correction at sea is required because of there is a deficiency of mass here in the ocean. So these are the formulas which I have just explained. We can calculate the theoretical gravity value using this formula. Then we subtract it from the observed gravity value after applying the correction. If we do not apply a Boger correction, then it is a free error anomaly. If we apply a Boger correction, it becomes a Boger anomaly, and Boger anomaly is the final product of output of the gravity survey. So this is a typical contour map which shows the Boger anomaly map. Boger anomaly sometimes is known as a Boger gravity also. So what we do that we take the gravimeter readings at two-dimensional first at this point, at this point, at this point, at this point, then along this direction also we measure the gravity value in a two-directional area, and then we calculate the Boger anomaly at every point, every site wherever we have taken the reading. Then we contour them. So once we contour them, this is the typical Boger gravity map of a region. Then we interpret in terms of the ore body, presence of the ore body, which will be available, which will be clear from the density contrast or from this one. So this is a isostasy. This is another application of the gravity survey that in mountain, because we know that the depth. Isostasy means that equilibrium of the crustal rocks. If you might have heard the Maho discontinuity, which separate the crust and the mantle. So the average depth of the Maho discontinuity is 33 kilometer. But in the below the mountain, it has been found that like in Himalaya, below the Himalaya, the thickness of the crust is around 70 kilometer. So it means that this can be explained by the isostasy, concept of the isostasy, that wherever there is a mountain, the low density material has gone deep inside the earth to compensate that excess mass which is there on the surface. So we can say that this is a isostatic compensation is there, or they are in the equilibrium. So these are the two models that explains the concept of the isostasy. So Boger anomaly will help us that whether the mountain is compensated by the mountain root or not in that area. So if Boger anomaly is 0, it means that it is uncompensated. It has not been compensated. But in this case, if there is a mountain, it is being compensated by the low density material going deep inside the earth. So it is a compensated excess of mass above sea level is compensated by the low density material below that. So by looking at the Boger anomaly, we can see that whether it is isostatically compensated or not compensated. This is also the same one in a different way. Then another feature of the Boger anomaly is that it tells us about the thickness of the crust in a particular area. For example, let us say this is a geological structure. This is a mountain, let us say, and this is the mean sea level, and this is the ocean, deficiency of mass. So we are conducting the gravity survey on this area, let us say. Okay, for example, that at this position we take the gravity value. So at this position, the contribution from the crust as well as all the masses are contributing in the reading of the gravimeter. So up to this level, the gravimeter reading, this level, the material which is lying between this point and this point, they are contributing to the reading of the gravimeter. So low density has a more effect on the gravimeter reading because thickness is here more as compared to the high density material. So that's why reading is low. So it means that when the thickness of the crust is more, reading becomes low. On the other hand, at this position, the high density material is more, low density material is less. So that's why the reading is high. So contribution of high density material is more in this case at this position C. So it means that Boger anomaly tells us about the thickness of the crust. Wherever the Boger anomaly is low, thickness of the crust is more. Wherever the Boger anomaly is high, the thickness of crust is less. So that is how, in addition to the ore body, Booger anomaly curve will also help us to have an idea about the thickness of the crust in that area. Then as far as interpretation is concerned, one more important point here is the which we call regional and residual gravity anomalies. So meaning thereby is that for example, in this case, when we conduct the gravity survey, our ore body is here, let us say spherical type ore body, but the contribution of the mass, because it is a natural source method, we have no control on the depth. Contribution of the mass which is lying between the position of the gravimeter up to the center. So they are also contributing in the reading of the gravimeter. But we are interested in the ore bodies only during gravity survey. So it means that the contribution from the shallow depths are also there in the gravimeter reading. From the deep depth also it is there. So that portion of the gravity anomaly, which is coming from the shallow depth, that we call a residual gravity anomaly. And that portion which is coming from the deeper depth, that is a regional gravity anomaly. So in a local gravity survey, we are interested in the residual gravity anomaly, not the regional one. So that's why before final interpretation, we have to separate them. That what is the residual one, which is coming from the shallow depth features, and what is the regional one, which is coming from the deeper depth features. And for the ore body exploration, we are not interested in the deeper depth. We are interested only at the shallow depth, because ore bodies are present up to, let us say, 4 kilometer, 10 kilometer, or 7 kilometer, but radius of the earth is 6400 kilometer. So we are not interested in knowing the gravity contribution which are coming from the deep features. So we are interested in the shallow one. So we have to remove the effect of the regional from the Booger anomaly. So that's why there are some methods, that is because Booger anomaly is a regional as well as residual. We are interested in the residual. We are not interested in the regional. For a local gravity survey, we have to remove the effect of the regional. For that, these are the methods, graphical methods, analytical methods are also there, direct computation, second derivative. Ultimately, just you keep in mind that in a Booger anomaly, there are two contributions. One contribution is from the deeper features of the earth. Another contribution is from the shallow features. Ore bodies are lying at the shallow depths. So we are interested in the shallow features. Shallow features is known as a residual gravity anomaly. So like this is because of some shallow feature, but it is being masked by the regional feature, which is coming from the deeper depth. So that becomes a noise for us. So we have to separate them, and these are the methods to separate the residual and the regional one. So this is just an example that this is our total gravity anomaly. Then we plot a regional. So when we subtract it, then we get the residual. So once we get the residual, then we can interpret that. What is the depth of the ore body? What is the dimension of the ore body? We can interpret in that way. So this is just another example that how to separate the residual and regional one from the Booger anomaly. So this was the original map, Booger gravity map. Then we plot the regional one, then we subtract it. Ultimately, this becomes our residual anomaly. Then for interpreting the gravity data, first of all, we should know that how the gravity profile looks like for a simple shapes body. Suppose that this is the ore body which is present in the subsurface. So this can be approximated by a sphere. This can be approximated by a simple shape, geometric shape sphere. This is another type of the geological body. This can be approximated by a vertical cylinder. This is another type of the ore body. This can be approximated by a combination of three spheres. So we want to know the gravity effect of a geometrical shape, which will help us in the interpretation. So like for a spherical ore body, if we drive the formula will be like this. For a spherical ore body, the gravity value can be written as this one, 4 pi r cube. Delta rho is the density contrast, Z is the depth of the ore body, X is the position of the gravimeter, this point, this point, this point, this point, and Z is the depth. So ultimately, for a spherical ore body, the gravity profile looks like this one. So wherever there is a ore body, this is our profile. For a spherical ore body, this is one. Then okay. Then for this is another, this is just a means explanation of the spherical ore body, that at x is equal to 0, the gravity becomes maximum. And as we move from the ore body here and there, then it decreases like this. So this B is for the spherical ore body B, and this A profile is for spherical. So naturally this spherical ore body is at a shallower depth as compared to the deeper depth. So the maximum value has decreased. So this is a typical shape of a gravity profile due to a spherical ore body. So when we go to the survey, do the gravity survey, we plot this type of the profile, and by looking at the shape of the profile, we can say that corresponding to which type of the ore body this profile is there. So this profile has been plotted after applying all the corrections, then after separating the residual from the regional one. So this is a typical, you can see here that this is typical spherical ore body for the different values of the density contrast and the Z, it can be like this. And this is for a horizontal cylinder. For horizontal cylinder, if there is a fold type structure, that can be approximated by a horizontal cylinder. So when we calculate a little bit trigonometry we use, and ultimately for horizontal cylinder, this will be the formula to calculate the gravity effect of a horizontal cylinder. And this is the typical shape. So if you compare it with the spherical ore body, you will find that in case of a spherical ore body, the width of the profile was not large as compared to the cylindrical one. For horizontal cylinder, the width is more, but for a spherical ore body, the width of the profile is less. Similarly, this is for vertical cylinder. We can derive some formula and plot the shape. And this is also for vertical cylinder. And ultimately, this is the summary of the formulas for the spherical ore body. This is the typical shape. And for a horizontal cylinder, this is the formula we can derive. And this is the typical shape of the gravity profile at the surface. And for vertical cylinder, this is the typical profile. So what is the advantage of these shapes, these profile? Because when we go to the field, we again plot the profile. So by looking at the shape of the profile, we can say that whether that profile is corresponding to a horizontal cylinder type body or it is corresponding to a spherical type ore body in the subsurface. So once we decide that this is because of a spherical type ore body, then we go for the interpretation, then we go for the depth as well as the depth determination and the dimension also. So this is for a typical horizontal slab. So when we go for ultimately, it will help us. I go to the next one, this one. This is a typical geometry that we call fault in the geology. So if there is a fault in the subsurface, then profile will be like this. Gravity profile will be like this. When there is a fault in the subsurface, this will be the gravity. So this is different from the spherical ore body, different from the cylindrical, horizontal as well as vertical. So by looking at the profile, field profile in actual way, we have to decide that corresponding to which type of the ore body or which type of the geological structure this profile is there. And then we can interpret that profile in terms of the depth, in terms of the dimension. So this is again gravity effect due to a fault. So all these are the mathematics. So we should not go in detail for the mathematical derivation. This is the interpretation. So once we know that gravity profile is because of the spherical ore body, then what we do, we note down the maximum value of the gravity. Then we come down to this axis. We note down the point where the maximum becomes half. So at this point, the maximum gravity value becomes half. Then this width of the profile is known as the half width. So this half width is related with the depth of the ore body. So this x half, we can note down from the profile of the gravity. What is the x half? X half is that value of the profile where the gravity maximum is half. So we note down this x half, multiply it by 1.3. It will give you the rough idea of the depth of the ore body. So from the profile, we can calculate the depth. So once we know the depth, we can calculate the dimension. Dimension means that we want to calculate the R, that is the radius of the ore body. Once we calculate the radius, then we can calculate the area. So why we are interested to know the aerial extent of the ore body? Because ultimately we have to decide that once ore body is present, whether we should go for mining or not in that area to extract the minerals. And mining is also a very costly business. And if the aerial extent of the ore body is not large, so it means that it will not be cost effective, because the expenditure on the mining will be more as compared to the actual value of the minerals which are there in the ore body. So that's why it is very important to know the dimension also, to know the aerial extent of the ore body also, that whether it is economically viable or not for mining in that area, for extracting the minerals in that area. So with the help of this, we can calculate the dimension, because Z we have estimated, and then this maximum value we can know from the profile, and then we can calculate the dimension. Similarly, for horizontal cylinder also, Z is given by the x half, and then we can calculate the dimension in this case. So this is the summary of the parameters, how we can estimate for a different types of the ore bodies. For a spherical ore body, we can calculate in this formula, depth is given by 1.3 x half, then we can calculate the dimension. For a horizontal cylinder, depth is directly x half. X half, remember that from the G maximum, we come to the half maximum, we note down the width of the profile, then we multiply with some constant to get the depth. So once we know the depth, all these are constant. G maximum can be read from the profile. We can calculate R. We have to assume the density contrast because we know the little bit density of the rock materials. Similarly, for vertical cylinder, it is like this one. So this will give us a rough idea of the depth and the dimension of the ore body. And ultimately, we go for this is one irregular ore bodies. Note down the slope of that profile in this case, and for 3D bodies, similarly, we can calculate depth. Depth is less than 0.65 and this ratio. So for irregular ore bodies, we apply such type of the formulas to interpret the gravity anomalies. And finally, there is an indirect interpretation. Whatever formula I have discussed, that is for the uh, broad idea or rough idea of the depth and the dimension. And finally, we go for the indirect interpretation. So in this case, what we do, this is our observed data, dotted one. Then we calculate using formula, theoretical formula, we calculate this one. Then we compare these two. So if they are not matching, then we change our parameters, density, contrast, depth, and the dimension to plot the calculated data again. So because observed data we cannot change, we go on changing the calculated data, we go on changing the values of the parameter until unless the theoretical value becomes the same as the observed value. So whatever parameters have been used to plot that theoretical value, which is matching with the observed one, those parameters can be fixed. Those parameters can be finalized. So in this case, this we call the indirect interpretation. So I think I have completed. This was my last slide. So I thank you all for listening me carefully and patiently. So if there is any doubt or any query, I would like to and I will try to satisfy that.
Yes, sir. There are some questions in chat box.
Okay, in chat box, let me see.
The first question is for electrical method, typically up to
Yes.
what depth probes are put inside the earth?
Actually, it depends on the source that for how many, what is the source of our electric current. If it is a large, then it may go up to the deeper depth. But for ground, because electrical method, the our main objective is to explore for the groundwater. So groundwater is up to 100 meter or 200 meter, depending on the area. So it is always at the shallow depth. So depth, you can say it may go up to 150 meter, the current, depending on the source which we are applying there. Because ultimately we have to send the current inside the earth through some electrode. Then we record the potential, and using the Ohm's law, we calculate the resistance, and from the resistance, we calculate the resistivity, and resistivity curve will give idea about the presence of the groundwater there.
Yeah. There is one another question.
Yeah.
Why air drag is not being considered in wet drop method and pendulum methods?
No, actually the PPT which I have shown, that depicts only the principle of the gravimeter. Ultimately, when gravimeter is designed, this system is in a thermostat box. There is no effect of temperature, effective very minimum. It is almost a vacuum type condition in the gravimeter. So whatever I have shown, that is just to depict the principle of the gravimeter, and that to the absolute gravity. It is always considered while designing the gravimeter. It is always there. It is always.
Uh, the next question, although it is not related to Earth, it mentions, does moon's and sun's gravity also changes and gravity measured? If yes, how to correct it?
Yes, definitely it changes, because if that student recall that tidal correction, I have given a little bit idea, drift correction and tidal correction. So tidal, because of the gravitational effect between moon and the earth, or between sun and the earth. Because whenever there are tides, the position of the gravimeter will change, distance will change from the center of the earth. And an important point for tides is that they are predictable. We can know that when the tides will be there and when there will be no tides. So what we do, when we apply the drift correction, we reoccupy the same station after regular interval of time to know that how much gravity value has been changed at the same place due to tides or due to the drift. So when we apply the drift correction, it will take care of the tidal effect also.
Yes, sir.
Is it clear to that person who has raised this question?
You can put the question in chat if it is not possible to talk to you.
Yeah.
By that time we'll take a next question.
Yeah.
The next question says, in gravity measurements, if there somehow a earthquake happens, then how it would affect the measurements during the measurement, suppose any other disturbances are there.
Yes, other disturbances are always noise for the gravity method. So if earthquake happens, let us say, because in earthquake, the ground will vibrate. So when ground will vibrate, the position of the gravimeter will change from the center of the earth. Distance will change. So that distance will change, then our reading will change. So definitely we have to reject that data. Means we cannot go for interpretation for that data. We have to go to that position again next day, so to measure the gravity value again. So ultimately, the purpose of all the corrections which I have discussed briefly, purpose of the correction is to remove all the factors which are changing the gravity value except one factor, that is the density contrast. So that is our signal. All other factors are noise. For every type of the noise, there are different corrections. So particularly in case of earthquake, we have to reject that data, because for that we cannot correct that data. We have to reoccupy that station after 2-3 days again to get the correct data.
Okay. Now the relative anomaly means whatever the difference we are measuring.
Yes.
It will be different for different minerals such as oil and gold, iron or ore, iron ore, and so on. The question says, typically for a good ore of say gold, how much gravity anomaly in order of magnitude, and for oil?
For oil?
Yeah.
Actually, the application of gravity for oil exploration is that first we look for the geological structures, fault, or some other structures which indicates the presence of the oil. So before going for a detailed seismic method for oil exploration, ONGC or any other company will go for a gravity survey. So the purpose of gravity survey for the oil exploration is that to locate for the geological structure. So
Right.
once it is a geological structure is there, fault or fault, then they go for the detailed survey seismic method, because seismic method in geophysics is a very costly as compared to the gravity method, gravity survey. So first we go for the gravity survey in oil exploration. So in that case, gravity method does not directly tell us that whether oil is not or there, oil is there or not. It will just tell us about the geological structure where there may be the possibility of oil is there. Then that can be confirmed using the seismic method, because gravity method will tell us about the because it will respond, gravimeter will respond only to the change in the density, change in the mass. So that will tell us about whether fault is there or not, or fault is there or not. Once it is there, then we can go for the oil exploration method. And as far as ore body is concerned, as I have given one example also, that the maximum value of the gravity in case of a different types of the rock bodies, it may be 0.25 milligauss in case of the ore bodies.
Yeah.
But,
The next question is, how are gravity anomaly measured for Moon or Mars by orbiting probes?
how gravity anomaly?
Are measured for Moon or Mars by orbiting probes.
By orbiting
Whether the
probe.
same method is used for Moon and Mars by orbiting probes.
Actually, as far as the gravimeter which we are using uh, at the surface of the earth, the gravimeter is on the ground, but we are doing the airborne gravity survey also. In airborne gravity survey, the gravimeter is on the moving platform on the aircraft. But in that case, it will respond only if the density contrast is high in the moon subsurface or in the orbital surface.
Sensitivity.
We have to measure only with the help of gravimeter only, but that gravimeter is in the moving position. So when it is in the moving position, we need one more correction that is known as a EOTOS correction. But principle is same. Same gravimeter will be there in the probe, which will measure the gravity value. Or if sometimes it is possible to install the gravimeter on the moon itself, on the surface of the moon, then it will be more appropriate to know about the interior of the earth using the gravity values. But at present it is not possible. So I think if they are measuring, they are putting the gravimeter in the probe itself.
Now the question says, which correction will you spell out that correction?
For moving, because when
Yeah.
gravity correction will be when the gravimeter is in the moving position, then we apply one correction, that is a EOTOS correction, which takes care of the rotation of that planet also, as well as the Earth also. For that, we apply EOTOS correction.
You wanted to know the spelling.
EOTOS is actually, it is a name of the scientist. EOTVOS.
What you mentioned in the methods, correction, drifts.
Yeah. EOTVOS, EOTOS correction.
Okay. Sir, one more question.
Yeah.
Profiling require large number of readings, and the gravimeter what you are using, they use the old spring mass method. Whether they are being electronic or made electronic, and have the provision of data acquisition methods, so that large amount of data will be collected.
Actually, what happens that the gravimeter is a little bit costly from any institution. It is, let us say, about 2 crores or 1.5 crore cost is there. If you want to cover more points in a less time, then always it is recommended that you purchase, let us say, 5 gravimeters. One party will go along one line, another party will go another line, third party will go another line. So in that way, we can gather the large amount of the data in less time. But in most of the cases, because it is a costly, gravimeter is costly, So there is only one gravimeter or maximum two gravimeter with one party. So that's why it takes some time. But if you want to cover more point, then one has to purchase more gravimeters. That is the only way.
Otherwise, for one, it will take multiple number of readings for multiple times.
Yes, what we do that we take the gravimeter to the field, we put it there in a position, take down the reading. It may take 10 to 15 minutes. Gravimeter is portable. Then we take the gravimeter, go to the next position after distance of 10 meter or 20 meter. Again, we put there. So every reading will take 10 to 15 minutes. So if there are, let us say, 20, 30 points along a profile, so it may take, let us say, 1 day to cover that point, cover that line. Only one line, but ultimately, when we do the gravity survey, we have to cover a area. So area means it may be 3 into 3 square kilometer or 4 into 4 or 4 into 5. Then it may take, let us say, 3 months or 4 months or sometimes 6 months also, because all the points cannot be covered in a day. There are some limitations also going to the field. Sometimes, like in some areas, in northeast area or some other areas, it is advisable that don't go in the evening hours in any area in that area. So they prefer to take the reading in the morning hours. So they are in the camp. They put a camp there, field camp. They every morning they go with the gravimeter, collect the data, come back. Next day again go to the field, collect the data, come back. So like that, it may take 6 or 7 months if area is large.
Yes. Okay. Any other? I don't think any other question is there in the chat now. So, friends, it was a very, very wonderful lecture put up in a very simple and lucid term, starting with the basic principles of physics and which are being employed for geophysics measurements, geophysical measurements. It was a nice presentation in the way in which he has taken gradually he has improved the depth of the topic and explain the terms where you require correction. For a particular example, I can give as a relative value. Why we need relative value? Why not absolute value? Because absolute value we generally normally used to measure with the help of simple experiments and so on. So these are the things which the students will have to pay very important pay attention to. Thank you, sir, because so many things you have explained. I will not repeat the thing, but I must thank you on behalf of Wilson College as well as the IAPT SRC 08B Mumbai. Thanks again for your visit, and we look forward for your same cooperation in future also. And
Thank you.
all the participants, thank you.
Thank you, sir. Thank you, Dr. Mohalle. Thank you, Dr. Mahesh, for inviting me. I also
Thank you,
enjoyed
sir.
delivering talk, and I thank to all the students also who have listened to my talk. Thank you.
Yes.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Mahesh, over to you.
Yeah, thank you, sir. Thank you, all participants. We will meet in the evening session at 4:30. Please join the link, same link, 4:15 onwards.
Fill up the feedback form.
And fill up the feedback form, which I have put here in the chat, also on our WhatsApp group. Shubham, we may stop recording and we can end the meeting.